Okay, so we'll make a start. Thanks everyone for coming. My name's Galium. I'm the CTO at Datalytyx, and the title of my presentation today is 99% of your data is worthless, but which 99%? That's a deliberately provocative title. No one likes to be told that 99% of the data is worthless. Hopefully by the time I finish, you'll understand the very least what I mean by that, even if you don't agree. But I'm also going to do a couple of other things today. I'm going to give you a little bit of information on what we're doing with IT and OT convergence, and I'll explain what that means. But I'm also going to be given, and I was given permission by my boss to do this, a little bit of a sneak peek at what we're working on for early 2020. This is the first time this has ever gone public, and we're pretty excited about it. And I'm going to demo it with an unofficial world record. This is absolutely truly live. This may well go wrong, but I'm going to try and do a world record data ingestion attempt at the end of this. And if it works, rounds of applause. If it doesn't work, we're trying something new. Okay, so as a company, we have three primary offerings. The section I'm going to talk about first is Galium, which is our smart IoT compression technology. The second part of the presentation is going to move more towards Palladium, which is our big data platform as a service. And we also have a set of managed services which underpins these technologies and a few other kind of select third-party technologies we use for special bespoke projects. As a company, our expertise is across most industries, but in the last year or two, we've really been focusing down on what we call heavily instrumented industries. These are industries where the edge, whether the edge is a truck, a car, a plane, a factory, an offshore oil rig, but anywhere the edge is generating vast amounts of data. These are heavily connected industries, you'll hear them, industrial IoT, Industry 4.0, but those are the sort of industries that we are working with, and you'll see why because of some of the technologies we have. Just to give you an idea of the few of the customers we work with, I'm not going to go through these, but you see there's a lot of names on there that you will recognize. Okay, so Gallium, smart IoT compression. Start out with the problem. Why did we build Gallium? This is a connected car. The data coming off this car should be allowing a highways agency to get a historical and real-time picture of the conditions of the road network all over the country and prioritizing their maintenance budget accordingly. If we could make a 1% improvement in the maintenance budget of the UK Highways Agency, that's worth about £250 million annually. This is a connected aircraft. The data coming off this aircraft should be allowing the airline to detect degenerative failures in flight and have an engineer and a spare part waiting at the gate to fix it and turn the aircraft around in an hour, as opposed to today, they find out when the aircraft lands and plugs in. It could then be 6, 7, 8 hours to find the right engineer and the right spare part, which means the aircraft has to be taken out of service, new aircraft to be brought in, lots of time, lots of cost, lots of fines, lots of unhappy customers. If we can make a 1% improvement in the ability for an airline to turn around aircraft with faults, that's worth £15 million annually, even to a small airline. This is a smart factory. The data coming off this production line or out the smart factory should be allowing the organization to pull equipment out for maintenance only and exactly when it's needed, not according to a particular calendar schedule and not according to a particular number of hours worked. If we can make a 1% improvement in the asset efficiency or the asset performance in a smart factory, that's worth about £3.5 million to a single factory. Now, everything I said had a lot of shoulds in it. The answer is today, unfortunately, the majority of these things are not happening. And there's two main reasons they're not happening. The first one is data acquisition. There's a huge amount of data being generated, and it's very hard to get it back. The second thing is, even when we've got the data back, there's a vast amount of data to process, and doing that efficiently and quickly is very, very difficult. So how do we help with Gallium? We take IoT time series sensor data, and these are just different ways of describing the same sort of data. It's the data you're familiar with. We take IoT time series data, we dramatically reduce its volume for around 100-fold savings in transport. So that means over the same connection, we can transport about 100 times more data for the same cost, for the same bandwidth, and around a 700 times performance in analytics on that data when it arrives back at a central location, while maintaining a guaranteed level of accuracy. So Gallium is effectively a lossy compression technology. It says we will sacrifice a very small amount of accuracy, but a small amount that we can quantify and guarantee for a very large gain in data reduction and data performance. And all of this is for business decision making. When we sit down in front of data, we do it because we're trying to make some sort of decision. Universally, no one sits down in front of data and just says, hey, I've got nothing better to do, I'm going to look at some pretty pictures. Everyone is trying to make some sort of decision, even if the decision is everything okay, is everything behaving normally. So the reason is guaranteed accuracy is so important is who's going to make a business decision on data with an unknown accuracy, with an unknown provenance. And the sad fact is, actually, we'll get into it, a lot of people are doing exactly that. So to explain how this decision-making works, we're going to take it out of the time series domain and look at a domain that everyone's familiar with. If I look at an image, if I look at the high-resolution image on the left, I can answer an increasingly specific set of questions pretty easily. Is it an animal? What species is it? What breed? Is it wearing a collar? But I can answer those questions equally well using a very low-fidelity version of the data. So immediately we've established, actually, yes, decision-making, answering questions, I don't need all of the information. I can do it, in this case, with 1%. Now, there's always someone who says, oh, okay, but what about a really specific question, like what color eyes does a dog have? I can't reasonably answer that using the data on the right. That's fine. Sometimes we need to jump into higher accuracy data. But when we do that, the lower accuracy has given us triangulation. We now know where in the data to look. So we don't have to look at all the high accuracy data. We can just look in a particular location. So we've been able to answer everything from very, very broad questions across a large amount of data to very specific questions on a small amount of data. We've been able to answer all of our questions, and we only use 2% of the overall data. Now, if we take this back into time series, how does this work? Let's take a baseline of 100 to 1 data reduction so we can compare methodologies. I've been doing time series data in network management, infrastructure management for over 20 years now, and for over 20 years, the answer to the question, I've got too much time series data to deal with, has always been the same. I average it. That's what we do. We collect it at 1 second resolution, then we average it to 30 seconds, and then we average it to a minute, and 5 minutes, and 10 minutes, and a month, and a year, and eventually it gets so low resolution it's not worth keeping, and we drop it off the end. But that has, for 20 years, been the answer. If I look at this, to explain this, the green line we're looking at here is the original data, the pink line is our derived data. There's a few well-known problems with averaging. The first one is, as we know the effect of averaging, it smooths out all the peaks and troughs and spikes and interesting bits. So we can see here, it's keeping the macro level picture, but a lot of the spikes and peaks and troughs are missing. Now, if this is vibration data off an aircraft engine spindle, I kind of want to know those peaks and troughs. Those are the things that are telling me, okay, there's going to be a problem with this engine in the next few hours. You need to divert the aircraft, or it's going to be in the next few weeks, but you need to replace the part. Those peaks and troughs and spikes are really critical parts of the data, and averaging loses them. The other problem with averaging is we have no guarantee of the accuracy of the output data with respect to the input. It might be that on certain data sets, accuracy gives us a great picture. It might be 95%. On other data sets, it might be 5%. We have no measure of the accuracy of the data, and if we can't measure the accuracy of the data, how are we going to make a business decision? If we compare that to Gallium, on the same data reduction, over 99% accuracy, the fit is dramatically better. We've still thrown away 99 data points in 100, but we've got a much, much closer fit. It's not a perfect fit, it's a 99% accuracy fit, but I've yet to have a customer tell me, you know what, I'd make a different business decision on the green line based on, than the pink line. If on that bottom line, if you'd make the same business decision using the pink line and the green line, by definition, the 99% of the data you threw away to get there is not necessary. So when I make a claim that 99% of your data is worthless, what I'm saying is, at least for time series data, if you can make the same business decision on 1% of the data, which the vast majority of the time you can, all of the time and effort and cost and expense for transporting, for storage and analyzing the other 99% is by definition worthless, because it wouldn't change the decision you would make. And Gartner calls this the MPEG or the JPEG of time series data, which is kind of a nice way to think about it. Who agrees with us? Well, the answer is actually a lot of people have identified the characteristics that we are exploiting. Microsoft talks about the high volume, all of the challenges, but then they even get to the point of saying you need to sacrifice some precision. But the answer when you come to the end of it is da-da-da-da, and you have to downsample. And that's what we're trying to get away from. We know the challenges of downsampling, of averaging. So where do we apply Gallium? There's two places that Gallium is used. The first one is at the edge, and this is really to solve the data acquisition problem. If we take a connected car with 20,000 metrics or an aircraft with 5,000 metrics, across cellular or satellite connectivity, there's no practical way to get that data back. You know, typically in a connected car case, people are pulling back 10, 20, 30 metrics of 20,000. But they're pulling them back at 100% accuracy. If we can put Gallium in the vehicle in the same bandwidth, we say rather than pulling back 20 metrics at 100% accuracy, why not pull back 500 or 1,000 or 2,000 metrics at 99% accuracy? Does that give more value to your business? And the answer, almost without exception, is yes. Once we brought it back, we can do exactly the same things as we would do, we're just sacrificing less than 1% precision. The other place we use Gallium is in the core. This is to solve the data analytics, data processing problem. So we've taken a 6.3 terabyte, 400 trillion row, or 400 trillion data point data set. It's not the biggest data set in the world, but it's pretty significant when you want to try and analyze it in one place. And we've done a comparison. On the right-hand side is what you would get today using pretty state-of-the-art technology. And we'll see as it comes up, it's nearly 2 hours to process on the left-hand side, sacrificing less than 1% accuracy. We did the same analysis in less than 10 seconds. So an hour and 48 minutes to 9 seconds, that's a 700 and some odd performance improvement for less than 1% drop in accuracy. 1% drop in accuracy, 700 times improvement in speed of getting our answers. That's a decision, a trade-off most people will make. But if that was the only problem we're trying to solve, that problem was solved 20 years ago. If it's a complex analytical problem, and all we're trying to produce is a static dashboard, we'll run it at 3 a.m., we'll let it run for 3 hours, we'll render it to a PDF, we'll email it to ourselves, and we'll see it when we get into the office. The challenge today on these large data sets is not generating a single report, it's not generating a single dashboard, it's what happens when that dashboard tells you something interesting. How do you move from the, that's interesting, to the, aha, there's some actionable information. And that process is data exploration. So data exploration, and we've taken that same data set now, and we're running, we're doing trend analysis, we're filtering out particular regions of the world, we're filtering particular countries, we're adjusting time windows. This is all on 4.5 trillion data points, and we're doing that in real time. Each one of these steps is taking 4, 5, 6 seconds on 4.5 trillion data points, real-time data exploration. No pre-aggregation, no requirement to predefine your queries, anything that's possible to do through the UI of whatever BI tool you're using is possible here. So ultimately we get 8 different exploration steps in 41 seconds. It's about 5 seconds per step. So where are we using this? All sorts of places. We're doing projects with merchant navy and military vessels. Drones are really interesting as people move beyond line of sight. A lot of offshore energy, wind, gas, oil. Satellite data acquisition, which is my background. Connected cars. We have a customer in the audience today. Very well-respected customer, very well-respected in the connected car space called Wejo, who are the market leaders in this area. Trains, agriculture, again, it's back to those heavily instrumented industries. Anywhere where it's heavily collected, you're collecting a lot of data, there's big value in deploying Gallium. So in conclusion, for the first piece of this presentation, 700 times speed up in analysis, 1% of the data for no loss of business value, complementary to all existing technologies. So everybody out on the show floor that's doing better and better jobs of doing their own compression, of doing their own performance, we absolutely layer on top of that. We are complementary to the existing products out there. There is no direct competition to what we're doing because we operate in a different way. With technologies like this, it makes it now truly possible to store everything forever, and not just store it, but to be able to get access to it. Why would you store 10 petabytes of historical data if you knew that the time to analyze that would have been tens of hours? If that can be turned into tens of seconds, now all of a sudden it's worth storing it because we know we can get access to the data afterwards. 100-fold reduction in bandwidth costs. Data agnostic. We don't have to tune Gallium, we don't have to pre-configure Gallium against any type of data. It has a machine learning component built in. It will learn the data as it goes to make itself more and more effective. And it works on everything from tiny IoT devices, which you can see working on a stand, all the way up to massive data lakes. So that's kind of the first piece that I wanted to talk about, which is Gallium and the IoT time series. There's a big overlap over the next year, or has been over the last year, and will be over the next year, with what Gartner call IT and OT convergence. So what do we mean by that? We take our Palladium technology. Palladium is a big data platform aimed at the IT space. It's aimed at people who are bringing in ERP, CRM, sales, production type data. That's been the IT space, and that's where a lot of people play. Gallium has been aimed at the operational technology. So this is data coming out of the line of business. So this is data off cars, data off wind turbines, data off ships and ship engines. And what Gartner described as the OT-IT convergence is saying there have been good point solutions in each of those areas for quite a long time now. But to drive real business value for these sort of organizations, you have to get that data into one place. And traditionally, the systems that do the IT piece well don't do the operational technologies. And the systems, the historians and whatever do the OT piece well, can't handle the IT data. So our Palladium product, which is our cloud-native data platform, it's infinitely elastic, which means that we can scale from the tiniest test data sets all the way up to terabytes and petabytes worth of data. It comes with expertise built in. So it's a monthly service that you pay for, and that includes access to our data scientists, our data engineers, our data architects. It includes our automated ingestion technology, which I'll be demonstrating in a minute. And it includes our sophisticated modeling technology, which again I'll be demonstrating. This has been Palladium as it existed for the last year, or developed over the last year. But what we've been doing is bringing those platforms together. So we've taken our technology, which is really fantastic at the IT space, and our technology, which is really fantastic at the IoT, the operational technology space, and we've brought them together to meet this IT-OT convergence problem. And we believe that launching at the beginning of next year, Palladium will be the first platform that can truly say it is an IT-OT converged platform. Okay, final piece. I promised a bit of a sneak peek at what we're doing next year. A little bit of background. If you notice when I built this diagram of Palladium, there was a building block, a Lego block at the bottom missing. And when I came into the data industry a year ago from the satellite industry, it's quite nice coming into the industry because you bring a whole bunch of new perspectives, but you don't have any of the preconceived ideas about the way things should be done. And my background for 20 years has been software development, software engineering, and there's a lot of things that go on in that industry that are just taken for granted. There's other tracks going on that talk about DevOps. To me, the kind of 5 key pieces here in the software development lifecycle. The first one is all about governance and change. You know, when we're developing software, someone's making a change, someone else is peer reviewing it, someone else is approving it, then it's going through a series of tests. Every point at that, we know who did what, when, and why. We have complete change control and governance. We've been building software for years and years and years to be maintainable. The days of monolithic software have gone. We start out with tiny functions. We build those into larger libraries. We build the libraries into components. Today we call them microservices. And then we assemble lots of these components together to form complex systems. So we're still achieving the same end goal, but we're doing it by building up, starting with very small pieces. Each piece does one thing well, and we're building them, and we're building them, and building them, building them. And that's been the pattern in software for a good 15 years. That makes it dramatically more maintainable. Testability. There isn't a software engineer out there that doesn't expect when they've made a line of code change to be able to click a button and just deploy that to a test environment to make sure it all works. That is an ANSI, that's a chip to play the game in the software development space. And when you put those things together, what you get is dramatically higher availability. So because you've got governance, because you've got multiple people checking on things, because you've got small atomic pieces of code that are very simple to understand and therefore very simple to modify and extend, because you've got the ability for engineers to test their code, then automated testing, what that gives you at the end of it is a platform that's much more highly available than it would have been before. And even when there is a problem with it, occasionally you deploy to production, there is a problem, we've got 2 options. Option 1, we roll back because everything is version controlled, everything is point in time recoverable. And if the problem comes down the line because someone bypassed the process and made a direct change to production, which does happen, it's hard to legislate against it completely, what do? You don't mess about with troubleshooting, who did what when. The first option is always, let me nuke whatever's there and let me rebuild it from the master branch, because that's always the safe approach. In the software world 15 years ago, as these things were developing, people were saying, well, it's a lot more steps, it's going to take a lot more time, we're going to be a lot less efficient. Actually, yes, there are more steps, but each step is simple, clear, and mostly automated. What we ended up with was software developers becoming dramatically more efficient. And if you look at a curve of software developer productivity over the last 15 years, it's just gone up and up and up and up and up. That actually is where the entire Agile movement came from. The entire Agile way of working originally came from and was enabled by these software development life cycles. So that's what I've been working with for 15 or 20 years. 7 or 8 years ago, we started taking our software into the cloud and virtualization, and we took all the same lessons that we'd got from that software development lifecycle and we'd applied them to infrastructure. And we called it infrastructure as code. And we got all the same benefits around governance, around maintainability, around testability, the ability to just press a button and deploy a complete new test set of infrastructure code and see how it works before we consider checking it in, before we considering taking it live. What was really surprising to me when I came into the data world was where we are in terms of this process. And the answer is, we've barely started. I go and work with a lot of pretty high-end, big, respectable household name customers who still tell me, yeah, our process is that we decide over email we're going to do something and then Fred makes the change to production. That to me, as a software development background and having a lot of infrastructure as code, the words Fred made a change in production scares the hell out of me. What happens if Fred goes home and that change breaks? How do we roll that back? How do we decide? How do we know what Fred did? How do we go and track what change was made when the system goes down? It's a very, very, very old school way of thinking about things. But there's a few complexities in bringing this model to the data world. That's what I've had my team working on for the last year. They've been away in the lab trying to bring fundamentally the techniques of true data DevOps to all the other things we've been doing. So create a complete end-to-end data platform, everything from ingestion, modeling, curation, calculation, all the way up to consumption by business users, and running everything as a proper, true Git workflow, using code control for everything, driving everything where the Git repo now becomes your source of truth and your center of the world, and things like your data warehouse now become an ephemeral implementation of that can be changed, can be rebuilt at a moment's notice. And rather than kind of talk about it in slide form, I'm going to do something risky, which is I'm going to try and demonstrate the actual net effect of this. So we're going to try and set an unofficial world record for automated data ingestion and modeling. So I will start this running and then I'll explain what's happening. Don't worry if you can't see at the back, I'll talk through what's happening. So we set out to ingest 100 separate databases. Some are big, some are small, some have lots of rows, some have lots of columns. We wanted to ingest 100 databases from nothing into a data warehouse and do business transformation modeling, and we want to do it in under 5 minutes. So let me jump back to this. Okay, so we started with a completely empty system. What does that mean? My data warehouse at this point is completely empty. There are no tables, there are no views, there are no schemas. I have an empty data warehouse. The system I'm running this on started empty. The only thing it had on was our ingestion agent and the access details for a Git repository. So when I said run, the first thing it did, you may have seen it, the first thing it did was connect to the Git repository and check out the master branch. Everything it needs to know came out of that master branch. So everything it needs to know to run this entire end-to-end process came out of a Git repository, was managed as code. It's now going through the process and it's doing 63 at the moment. It's going through the process of discovering 100 on-prem, it's actually private cloud, but the point is these are behind firewalls. These are not publicly available things. There's a lot of technologies out there that do things like this, but they require access from the public internet. For most enterprises, that's a security no-no. You have to have an agent inside the network that's talking on a private network, and then you can send the results back, that's fine, but you're going the right way through the firewall. So we're doing discovery, we're connecting, we're discovering what schemas they got, what tables they got, what columns they got, what data types they got, what foreign keys they got. We're building a complete model of those databases. We're transforming them into a standardized schema for our data lake and our data warehouse. We're then doing full table loads. Because this has started from scratch, I've got no historical data to rely on. So we are pulling everything from the source systems. We're following an ELT model, so we're doing extract, load, transform, but there is no such thing as a true ELT model. Certainly if you've got anything with PII or information subject to governance, there are certain things that you have to transform on the way out because they can't leave the network. So in the process here, we're doing minimum transforms, but we're doing things like masking credit card information, potentially hashing email addresses. We're doing the minimum set of transforms on that data. Then we're persisting it to our data lake. We're then hydrating from that data lake into a data warehouse. We're using Snowflake for the purposes of this. And then once that data is in there and ingested as raw data, it still looks very much like the source systems. So every source table, every source column will have a one-for-one replica in our ingestion layer. We then need to do some work to transform that from a whole set of source silos into what the business needs. So that's the process. We move it from the ingestion layer, through the curation layer, to the calculation layer, to the consumption layer, and as we go up, we transform it from source silos into business marts. This is what the business, the finance department, the HR department, the operations department actually need. And when we finish this, we will have a fully running data warehouse that's not a one-time thing. If we just left this running, it's now done the full one-time ingestion, it'll now start doing incremental updates. So it won't have to redo this full ingestion, it'll now just start saying every minute or every second or whatever I ask it to do, just pull the new data in. And okay, we've now finished. So let's just check the results here. 100 databases analyzed, 1,400 give or take tables ingested, 14,500 columns ingested, 100% of our business modeling all the way through has been successful. And we've ingested a total of 103.4 million rows. We set ourselves a target of 300 seconds, 5 minutes. We did it in 183 seconds. So let's just wrap up a little bit what we looked at. First of all, this is the power of full metadata-led ingestion. If you go to a traditional approach for data ingestion, individual sources to ingest are measured in days or weeks. We did 100 of them in about 3 minutes. We've seen the value of really high performance modeling and transformation. We were able to take source data in a way that's only understandable by those source systems and transform it into business data that's understandable by the business. Obviously, the business mapping is something you have to do. We assume fairly simple models here. That would be a process that you'd iteratively go through as you're building up your business layers. That's not something that can be automated because that requires knowledge of the business, but it's still, all of the knowledge is ultimately then captured in a set of models, stored in the Git repository, and pushed in exactly the way I just did here. We obviously have to have a highly elastic platform. Both our ingestion platform, our modeling platform, and also our data lake and our data warehouse, in this case Snowflake, have to be highly elastic. You can't go from nothing to ingesting, best part of 1 million rows a second and 100 tables a second without a very, very elastic platform. And the entire thing was delivered as code. So we started out with a blank data warehouse, a blank ingestion box with a bit of software, and a Git repository, and that was it. At the end of it, we achieved what for most organizations would be a fully functional data warehouse, fully populated, now moving from one-time ingestion mode into incremental load mode. So this is what we've been working on. This is what's in the lab. This is being launched as what we believe is the first true data DevOps platform in the world in early 2020. There's lots of people out there that have individual component solutions, but in terms of a single platform that manages everything from cloud sources, batch on-premise sources, real-time sources, all the way through up to consumption by the business and managing everything in between, we believe this is the first true data DevOps platform. If you're interested, come and talk to us on our stand. We can't talk too much more about it. We've got some limitations until it actually launches, but we'll be happy to communicate as much as we can. And with that, I thank you for coming. I thank the demo gods for smiling on me today. Any questions? Either now or I'll be happy at the end. So there's a question. Apparently I have to put these on to here.